We are recording this meeting now. Any questions, comments, suggestions? Okay. So there's something that I wanted to discuss, that is the concept of path connectedness. So if you have no questions, then maybe I should do that. I'll give you a minute. You have something to ask, please do. Okay, we have more students. We have Akshay, we have Kritika, and we have Raika also have joined. Any questions?
Ma'am?
Yes, please.
Ma'am, this week there will be no assignment.
There will be no assignment now on. Yeah,
But
for this
ma'am,
week
can
also,
you
and for the following.
just problem set so that we can practice that before the exam?
Oh,
We
I
don't have.
will be happy to give it. Oh, I'll be happy to give the problem set. I thought you are already overburdened, so I did not. I will be happy to. I will post it, surely.
Okay, ma'am.
All right. Surely.
Ma'am,
Yes, please.
could you please discuss question number 5 of assignment 7?
Let me look up. What is question number 5? Okay. The function is continuous if and only if the graph of the function is a compact set in R2, right? So let's do this. So let's try. Somehow this is not working. I need to sort of close this and start again. So what are you given? You are given a continuous function defined on a closed and bounded set, correct? And you consider the graph of the function, and you are required to explore if there is a relation between the continuity of the function and a compactness of a graph. Now, graph happens to be a subset of R2, right? So do we know a characterization of compactness for Euclidean sets in R2? I don't know why. Yeah, why this is not working. Let me just try one more time, unplug all of this and see. Yeah. So in R2 also, much like R, we stated it without proof. Exactly the same proof works, that the Heine-Borel theorem works, right? Which means that closed rectangles are compact subsets of R2. Yeah, which in particular implies that closed and bounded subsets of R2 are compact. The converse is always true, which means to say that compact sets are always closed and bounded. That would imply that a subset of R2 is compact if and only if it is closed and bounded. Correct? So let's use that. Let's use that to use the, to assert the compactness of the graph of it. Yeah. Let's see this time if this works. Sorry. So let's see. Now it is working. Yeah. Sorry. All right. So this is question number 5. Assignment 7, right? So let f be a function from closed interval ab to r, correct? And the graph of f is the set of points x comma fx, where x varies in the domain of definition of f, right? So this is a subset of R2, clearly, correct? Correct? Is that okay? Now,
Yes, ma'am.
yes. Now, what are you required to show? That f is continuous on the interval AB if and only if G subset of R2 is compact. Okay. What is the first thing that we know? Suppose that, let's look at one way. Yeah, let's look at, let's assume that f is continuous, and let's try to prove that G is compact, right? So if f is continuous, that implies what? Closed interval AB is a compact subset of R. So what does it imply? It implies that the image of the interval AB, closed interval AB, closed and bounded interval AB under F would be a continuous function. Yeah. So let's sort of do it this way. Yeah. I think a neater way would be to do the following. Let's define. Let me define another function. Yeah. So let's define. So let's assume that let f be continuous on the interval AB, and we will show that the graph of f is compact. Okay. So let me do the following. Yeah. So let's define another map phi. Let's define. So this is a map from. This is a function from closed and bounded interval AB into R2. And how am I going to define phi? I'm going to send x to x comma fx. Now, if f is continuous on the interval AB, that would imply that phi is continuous, right? On the interval AB, right? Is that correct? Is everybody with me?
Yes, ma'am.
Yes. So, one way to sort of see this is that use the sequential criteria, right? Suppose that you have a sequence of points converging to a point in the interval AB, then right? Then you look at the sequence phi of xn, that would be xn fxn. This is a tuple xn fxn, and this would converge to x comma fx. Why is that? Since f is continuous by assumption. So the upshot of this discussion is that then phi is a continuous function on the interval AB, and why did I consider phi? What is the set G? What is the graph of F? The graph of F is by definition the image of phi under the interval AB. Is that correct? Is everybody with me on this?
Yes, ma'am.
Yes. So since the interval AB is compact, its image phi of AB is also going to be a compact set under the continuous function. Yeah. So let me just write down. Since interval AB is compact, its image phi of the interval AB, which is precisely the graph of F under the continuous function G, is also going to be compact, because a compact continuous function takes compact sets onto compact sets. Yeah, under the continuous function phi is compact. Correct? Yes. So this shows that one part of the question is done, that if F is continuous, then G is compact. Correct? How do you show the other part? That's what it says, right? You have to show both the parts, or there's only one part that is required. Let me see. Question number 5. Yeah, both. It's an if and only if statement that you're required to establish. Yeah. So now, so this part is okay with everybody present here?
Yes, ma'am.
Yes.
Yes.
So now let's look at this. Yeah. Conversely, suppose that G subset of R2 is compact. Yeah. So what is, remind ourselves, what is G? G is the following set. The graph of F is compact. We need to show that F is a continuous function. How do we do this? Somebody has some suggestions? Yeah, I'll give you a few minutes to think about it. But I would like, some one of you to sort of volunteer and help us out here. Which definition of continuity shall we use?
Hello, ma'am.
Yes, please.
Ma'am, if we say that f is not continuous at point P,
Okay. And then what do we try to do?
then we can say that there is a sequence that there
The
is a
se-
sequence that does not converge to a point in AB.
um, let's see if this will work. Yeah, let me write it down. So is that Sanjeet? Yeah, let's see. So here's a suggestion by Sanjeet. Uh, right. Suppose f fails to be continuous at P. At P belonging to the interval AB, then what happens? Then you are saying use the sequential criteria. Yeah, then there is a sequence of points in the interval AB such that xn converges to P, but f of xn, the sequence f of xn does not converge to f of P. Is that what you're saying,
Yes, ma'am.
Sanjeev? Yeah. Then how do we arrive at a contradiction? You may be right. Go ahead. Go ahead.
Ma'am, then we
Hmm.
define another sequence in R2.
Hmm.
Uh,
You look at the sequence xfxn, right? Is that what you want to do, Sanjeev?
yes, ma'am.
Xn fxn. Okay, then let's look at the sequence xn fxn. Then what do you do? Then what do you do with this sequence? This is a sequence in G,
Yes, ma'am.
right? Then what do you do?
Now, since G is compact,
Right.
there is a subsequence
Yes.
which converges to a point.
So
Uh,
every sequence in G has a subsequence that converges to a point in G. Yeah. So let me write it down. Yeah. Very good. Since G is compact, uh, this every sequence in G has a subsequence that converges to a point in G. In particular, so this is a sequence of points. Yeah, the sequence fxn has a subsequence. So let's give that subsequence a name. So let's call it xnk, fxnk, that converges to a point in key, to a point in G. Correct? Yes?
yes, ma'am.
Yes. Now what do we do?
Now we know that PFP is a point in G.
Uh, we know that PFP is a point in G. Certainly that is true.
So
So, we can use this, that xnk fxnk is a sequence that converges to a point in G, and G has a Euclidean metric, which means that, so let's say, suppose this is the point AFA. Yeah, well, not A already we have A star. For some A star in the interval AB, correct? So then by the convergence, by the definition of the Euclidean metric in R2, it follows that x and k would converge to A star, and f x and k must converge to f A star. Is that correct? This
yes,
is the
ma'am.
definition of the convergence in the Euclidean metric, right? Is that okay? Everybody remembers that? But what can we say about A star? See, the sequence xn converges to P, and xnk is a subsequence of xn. So A star must be the point P by the uniqueness of limits. Is that correct?
Yes, ma'am.
Yeah, is everybody with me on this?
Yes, ma'am.
Yes. Now, since xn converges to P by assumption, and x and k is a subsequence of the sequence xn, we must have, what do we have? We must have A star cannot be anything else but the point P. So f, x, and k must converge to, so this implies that, what does it imply? This implies that f a star is nothing but f of P. Now, how do we sort of conclude the argument from this point? So this is saying, let me just remind you, where are we? That the subsequence fn, fx and k converges to fp as we allow k to tend to infinity. Then how do we sort of complete the argument?
Ma'am, we had assumed that fxn does not converge to fp.
Correct.
So, but we have a
But fx
sequence.
and k, yeah, subsequent, yeah, that converges to f of p.
So
Are
we
we
get
done?
contradiction.
Okay, I will sort of leave it for you to figure out. I think this is a good enough hint. Yeah, very good, Sanjeev. Please complete the argument from this point. So is this okay? I think Kritika, you asked this question. Is this okay?
Yes, ma'am.
Yes. Okay. Excellent. All right. Anything else that you wanted to ask? Some other comments, suggestions? Okay. If there is nothing, then I would like to discuss path connectedness. How many of you are here? Some 5 of you. Let me just, I will not do something very complicated, but I thought it's a new concept. So instead of introducing it in a practice problem sheet, it might be good to spend some 5 minutes discussing it here. Path connectedness. Okay. So before path connectedness, what is a path? Yeah. So let X be a metric space. So X means XD is a metric space. X is a set and D is a metric on X. A path in X. What is a path in X? A path in X is a continuous function let's say R from the interval 0, 1 into X. Yeah. So, right. Sorry, I don't know what happened. So this is a continuous function from the interval 0, 1 into X, right? And what is the meaning of path connectedness? Path connectedness means the following. So when do we say a set is path connected? Here's another definition. So I have not, sort of strike this off, but somehow this box was created. So let me just write it neatly. So this is a function, yeah. So let's say R from 0, 1 into X. Yeah. So X is said to be path connected if for any 2 points x1 and x2 in X, there is a path joining x1 and x2 that lies completely inside X. Yeah, there is a path so let's give this a name. Yeah, so there's a path sigma in X joining x1 and x2. Yeah. So what does that mean? It means that this is exactly saying that there is a continuous function from the interval 0, 1 into x such that x1 and x2 are in the range of sigma. Yeah? So which means that, you know, one can always sort of reparameterize sigma to say that sigma of 0 is x1 and sigma of 1 is x2. Is that okay? Now, no matter what 2 points x1 and x2 are, there is always a path joining x1 and x2. Right? I'll give you an example. Is this definition is okay? Everybody with me up till this point? Is that a yes with everybody present here?
Yes.
Yes. So let's take an example.
Yes, ma'am.
Yeah. Yeah. Let's take an example in R2. Yeah. Or maybe start with R. Yeah. So let's take the first example. That let's take interval 4, 5. Yeah. So this is 4 is somewhere here and this is 5. Yeah. So this is 4 and this is 5. I say that intervals in R are path connected sets. So, you know, I could have taken open interval 4, 5, open 4, close 5, close 4, open 5, doesn't matter. Yeah. As far as path connectedness is concerned, intervals in R are path connected. Yeah. So, you know, you pick any point, any 2 points in this interval. So let's say this is my point x1 and this is my point x2. You can always find a map from closed interval 0, 1 into the interval 4, 5 such that 0 is taken to x1 and 1 is taken to x2. Surely, is that true? You just like the equation of the straight line segment joining x1 and x2. Is that correct? Is everybody with me on this?
Yes, ma'am.
Yes. However, if I take this example, yeah, let's take another example. Let's look at the interval 1, 2 union the interval 3, 4. I say that this is not path connected. Why is that? So let's see, what is it? So I have maybe 1 here and I have 2 here. I have 3 here and 4 here. Yeah, so my set is this 1, 2 union 3, 4. Right. So I am saying that this is not path connected. So I say that let's pick x1 to be here and x2 to be here. Then there is no continuous, there's no path joining x1 and x2 in this set. Yeah. So I say that this is not path connected. So let's say pick x1 in the interval 1, 2, your favorite point, any, and x2 in the interval 3, 4. Then there is no path sigma from the interval 0, 1 into 1, 2 union 3, 4. joining x1 and x2, yeah, such that sigma 0 is x1 and sigma 1 is x2. Can anybody help me out? Why is this the case?
Ma'am, because 2 to 3 is not present in the set, so if we consider any path
Right. So you sort of, how do you, right, so you are right, Kritika, but how do you sort of justify it rigorously? That's the idea. See, the point here is that we require sigma to be continuous. We require sigma to be a continuous function from interval 0, 1 into interval 1, 2 union interval 3, 4, such that at 0, sigma takes 0 to x1 and 1 to x2. So how do we argue rigorously? Why is this not possible? Why is this not possible?
Ma'am,
Yes, please.
ma'am, the interval 1, 2, union 3, 4 is not connected.
Sure, then what happens?
And since 0, 1, we know that for means if it is a continuous function, means a continuous function takes a connected set to connected set. Since
Correct.
1 to union 3, 4 is not connected, but 0, 1 is connected. That's why it is not continuous.
Was there like sigma union 3, 4? Sigma is allowed to be a map into this. All it requires it that 0 must be taken to x1 and 1 must be taken to the point x2. Right. So what I'm trying to say is that, meaning the your idea is correct. You use the fact that the interval 0, 1 is connected and sigma is, so suppose there is, so we argue like this. Suppose there is a path sigma which takes 0 to x1 and 1 to x2 such that sigma takes continuously the interval 0, 1, closed and bounded interval 0, 1 into interval 1, 2 union 3, 4. Now, since 0, 1 is connected and sigma is continuous, the image of sigma, which is the range of sigma, is also going to be a connected subset of this set 1, 2 union 3, 4. However, the image has to contain the points x1 and x2. If fairly, so let me just write it down clearly. Maybe I think it's just too much to process orally. So if there were a continuous, let me not write continuous. A path means it is continuous by definition. If there were a path sigma from the interval 0, 1 into 1, 2 union 3, 4, such that sigma joins the points x1 and x2, then the image of the interval 0, 1 under sigma is a connected subset of this, right? Is connected, right? Yes, please.
Ma'am, are you writing?
Yes, can't you see this?
No, ma'am.
So is this the case with everybody?
Yes, ma'am. Yes, ma'am. We are
Oh, no, nobody
noting.
can say? I don't know what
No, ma'am.
happened suddenly. So let me just save this file, close this window and open it again. Maybe it will work. It will reconnect again. Yes. But you were able to see earlier?
Yes, ma'am. Up
Yes,
to
Yes.
sigma 1 is equal to x2, it's written.
Only that is written. I don't know. See, the internet is working fine at my end. Let me just close this tab and open again. Maybe it works. Yeah. Uh, let's see. Okay. So now can you see? So I've written if there were a path sigma from interval 0, 1 into this. Can you see something now? Such that sigma 0 is x1, sigma 1 is x2. And then the image of sigma under the interval 0, 1 is connected.
No, ma'am.
no, ma'am.
No.
No, ma'am.
See, what could be the issue? Okay, so let me write again. Maybe that will help. But you can see the screen, yeah? I closed the window and I opened it again.
Ma'am, the screen has frozen.
Screen has frozen. Uh, so maybe, why don't all of you sort of log out and log in again? Maybe that will help.
Yes, ma'am.
Okay, ma'am.
Yeah, try. Please try that. Please let me know when you're back. Are you all back in this meeting?
Yes,
Yes.
ma'am.
Yeah.
Yes, ma'am.
So is this working now at your end?
Ma'am, there is
Ma'am,
no
we can't.
screen.
There is no screen.
Oh, there's no screen. So let me sort of start sharing again. Maybe it will work. Uh, so now I am sharing the screen again. This is rather strange. Anyways, so do you see it now?
Yes, ma'am.
Oh, excellent. Wonderful. So Raika, you were almost there. What is that I wanted to say here? That sigma need not be onto. So we don't require. We are using the fact that the interval 1 2 union 3 4 is not connected, but the argument is slightly tweaked. So if there a path in intervals 1 2 union interval 3 4 joining x1 and x2, then the image sigma 0 1 is connected. Yeah, now this is a connected subset of R, so hence it follows that sigma 0 1 is an interval in R, right? Because the only connected subsets of R are intervals. Is that correct?
Yes, ma'am.
Yes. However, we reach a contradiction because x1, x2 both belong to the range of sigma. However, if you pick a point y of so you pick a point y in the interval x1 x2. Yeah, so what am I going to do? I'm going to pick y somewhere here. Yeah, so y is a point in the interval x1 x2, and y is also between 2 and 3. Yeah, so let me write it in this manner. However, if you pick y such that y is less than or equal to 2 and 3, and y is well, I want a strict inequality somewhere. Yeah, so I'll take so x1 and x2 are both allowed to be equal to 2 and 3 respectively. So let me put a strict inequality here. Yeah, here between 2 and 3. So pick y like this. So y right, but y does not belong to the image of this. Why is that? Because by definition the image of sigma lies inside the interval since sigma is a map from this into 1 2 union 3 4, right? So x1 and x2 both belong to this interval. So let me call this I floor. So this cannot happen, that I have an interval I, x1 and x2 both belong to I. However, y is an intermediate point and y does not belong to I. That cannot happen if I were an interval, right? So Raika, what I wanted to emphasize here is we are using the fact that this 1 2 union 3 4 is not an interval, but not exactly in the manner that you said. Is that okay? Do you get my point, Raika?
Yes, ma'am.
Yes. See, because sigma need not be onto, right? In fact, sigma cannot be onto. Why? Because a continuous function always takes connected sets onto connected sets. But even this is not possible. Is that okay? Yeah. So all I wanted to illustrate by this is giving you an example of a set which is not path connected. So this was the story for the real life, right? So let's maybe in the remaining 2 minutes, I will just give you an example of a subset of, let's say, R2. Let's consider examples and non-examples in R2. See, path connectedness, unlike connectedness, is very visual. You can geometrically analyze it. So it's sort of gives you a feeling, you know, whether a set is connected or not, right? So let's consider R2 minus the origin. Yeah, so this is R2 and I have taken off the origin. This point is not there, right? So the question is to investigate whether or not this set is connected or not, right? So you pick any point x1 and x2 in R2 minus 0. Yeah, all you required is neither of these points are the origin. You can always find a continuous function from the interval 0, 1 into R2 minus 0 joining x1 and x2. Yeah, so this sort of dotted points that I have drawn is just the image of sigma, right? This can always be done, right? Everybody agrees with me that this is a path connected subset?
Yes, ma'am.
Yes. On the other hand, let me take another example of a subset which is not path connected in R2. Yeah, so let's take the disks. So let's take so this is all the points in R2. So let me draw a picture first and then let me try to write it down rigorously. Yeah. So suppose that this is the point 1 and this is the point minus 1. So let me consider this disk. So let me give this some radius. So let me give this radius half. So let me take my set to be the union of these two disks. Yeah. So what does it mean? It means so x minus 1. So let me not sort of do it analytically, and I don't want to be overshooting my time today. Yeah. So let's see. So what is this? These two disks is what my set is. I say that this is an example of a set which is not path connected. Why? Because if you pick a point here, x1, and another point, x2, there is no way that I can find sigma which takes continuously the interval 0, 1 into this set E, yeah, which is this union of these two shaded regions, such that 0 is mapped onto x1 and 1 is mapped onto x2. Yeah. This union of these two sets is not path connected. This is much like the argument which we use to show that the interval 1, 2 union interval 3, 4 is not connected. Is that okay? Does everybody understand this bit why this is not a connected set?
Yes, ma'am.
Yes, is that yes? Well, this is not a path connected set. I am yet to say how are connectedness and path connectedness interrelated, but this is not an example of a set which is not path connected in R2. Right? I think I'll just stop right here for now.